Great. So you are welcome, and thank you for being part of the lecture. I think we are making progress, even though slowly. So let me share my screen, but be able to. So we are making progress, and I think we have covered about 4 or 5 machine learning algorithms. Even in best subset selection regression, you have other small ones like stepwise, forward, backward, and so on. So we are looking at the logistic regression today, and I'm happy that those who attempted the pre-lecture quiz actually made it clear that it's not going to be a difficult discussion. So I also know that most of you are quite familiar with the technique, just like a few other ones that we discussed. So, but there will always be a new thing that will come up. So let's share it. For those who have looked at the material, it's quite extensive and is deliberate, even for most of the topics. So my ultimate plan is to make all this one to be a well-packaged written study material. So logistic regression, you may have known, is a powerful statistical method and mostly used for modeling binary outcome variables. Binary outcome variables, they have two levels. So generally, as you know, you have your dependent variable in any regression modeling, and you have your independent variables. The model you choose for analyzing your data will depend on the level of measurement of the dependent variable. As you know, the level of measurement could be continuous. It could also be discrete. So in other words, it could be discrete. So if it's discrete, then you could have binary outcomes. You can have multi-level outcomes. So, in other words, you could have 3 or more levels of outcomes. You could also have dependent variable that are based on counts. So you could also have those that are based on truncation, quite a number of them. So, but our focus, mainly for this. So if the outcome or the dependent variable is measured on a continuous scale. So that's when you use the linear regression model. But when the dependent variable is discrete, which means it's categorical, and it could be 2 levels and then 3 or more levels. So if it's 2, then linear regression will no longer be appropriate. So that's when you use the logistic regression. So for 3 or more, you also use logistic regression. But for 2, that's the one you call the binary logistic regression. So in other words, this logistic regression can also be is applicable to 3 or more dependent variable with 3 or more levels. So our focus in this discussion, in our lecture today, is binary logistic regression. So if you have a dependent variable, you have a dependent variable that has discrete value, let's say it's y, but it can only take 2 values. So y can only take 2 values, maybe yes or no, maybe fail or pass, maybe survive or dead, and so on like that. So there are so many of them, so you can also think of several other situations where you can experience binary outcomes. Exchange rate, for instance, will either be that it appreciates, so you can talk of appreciation, or depreciation. I know for those in the stock market, you also talk of the bull and the Dr. Lokere, is it the horn and the bull?
The bull and the bear.
The bull and the bear. So, so you can have the bull and you can also have the bear.
Or
So,
bullish and bearish.
and so on. Bullish and bearish. So, the truth about life is that most situations, most practical situations is either go or no go. It's either defective, not defective. It's either you win your election or you lose your election. It's either a child is born alive or is born dead. Can you also think of many other ones? Blessing, let me start with you. Blessing, think of other
It's either
binary.
you pass an exam or you fail.
I've already mentioned that. So it's either you pass exam or you fail. Uh, uh, if you are still thinking, maybe I will think more for you. I want all of us.
It's either you are sick or you are well, elsewise.
Okay. So it's either you are uh, medically fit or medically unfit. So the medical doctor can declare you medically fit or not medically fit. Yes, Femi is in a hurry to say something.
According to Nigeria situation, it's either you
Yes.
stay or you travel.
It's
It's
either
either
you,
it's either you stay or
yes.
you move.
It's either you stay or move. No, let me get you clear, very clearly. Femi. But
When
you
it
used
comes
to see no standing, no waiting, no loitering. So keep moving. So in that case, you don't have option. Keep moving. So it's only one, it's only one outcome. But, but as human, it's either you sit or you stand. You can. I'm sure most of you are sitting down, but I'm standing up. So it's either as you are receiving this lecture, it's either you are seated or you are standing. Anyway, the issue is that there are so many uh, economic situation, political situation, uh, educational phenomenon, social phenomenon. No, it's either uh, it's either you have rain or the rain, there is no rain. So you have many things in life that will only take two possible outcomes. For those who give birth, you either give birth to a male or a female. So in situations like this, if you are modeling any outcome with binary, any binary outcome, if you are modeling it, then logistic regression is the most ideal. So the key thing the key objectives, for this topic are understand the theory behind logistic regression and its applications. So we are going to look at the mathematical foundation of the logistic regression. And then we will also learn how we can develop logistic regression model in R. So you will see the R snippet, the output for implementing logistic regression, and even be able to interpret the outcome. So you gain skills in the interpretation of the logistic regression output. Then, of course, the ultimate objective is for you to be able to apply logistic regression to real-world data sets to be able to evaluate model performance. So, in the university, for instance, it's either an applicant is admitted or is not admitted. So there are so many areas where you can venture into as far as the application is concerned. We will also look at more specific application areas in the course of the lecture, particularly in the banking sector, in the health sector, and so on. So what is logistic regression? I've talked about that. Is a regression that is basically used to model binary outcomes, so such as pass or fail, win or lose, alive or dead, healthy or sick. So the outcomes are just two possible outcomes. Just two possible outcomes. So what that means is that logistic regression in a way will be calculating probability that one out of this outcome, which you will consider as success. So if let's say we are interested in exchange rates, so if our concern is exchange rate, for instance, which would be that it is going to appreciate or it is going to depreciate. So we can be interested in the probability, whichever to us we consider as a success. So we can consider appreciation as a success. So which means we are looking at probability of exchange rate taking appreciation. So that probability, as you know, probability lies between 0 and 1. You expect that the probability of the exchange rate appreciating plus the probability of exchange rate depreciating, since they are mutually exclusive, they have to add up to 1. So, but the point being made here is that because you have two possible outcomes, so the model is actually calculating the probability that an outcome will occur. So that is why that's one advantage, one of the major advantages of logistic regression, unlike linear regression. Logistic regression is actually modeling probability that and one of the outcomes will occur. So regression model does not model probability. It actually it models the actual observation, not the probability of the observation occurring. So so that's one major. So each object you are trying to the two, like I said, the probability must lie between 0 and 1. So logistic regression calculates this probability, and it tells you the likelihood of a particular, one out of the two possible levels, the probability of that particular one occurring. So as far as the difference between logistic and linear regression are concerned, there are two main differences. One is in the outcome variable. The outcome variable, which is our dependent variable, is a binary outcome. So in the linear regression, the outcome variable is a continuous outcome. It's measured on the continuous scale. Income is measured on the continuous scale. Weight is measured on the continuous scale. GDP is measured. Inflation is measured. So they are not discrete, but you can discretize them if you so wish. So, the second difference is the transformation function. So the transformation function uses the logistic function so that it will force the outcome variable to lie between 0 and 1. So, and on that basis, it is now possible to talk about, to model, and estimate probability from the. So, whereas linear regression uses the linear function, we know the linear function. Logistic regression, on the other hand, uses the logistic function, and we are going to see the logistic function very shortly. So these are two main, two key distinctions between the linear regression and the logistic regression. With respect to application, we've discussed a number of them, whether medical fit, so you are talk of the likelihood of a patient having a disease, in credit scoring in most banks. So customers, they apply for loan, they apply for credit, so to avoid the risk of cost of the applicant not repaying. So there is logistic regression is also used to estimate, their credit worthiness, the probability that they will default or not default. It's also used in marketing to predict customer retention, whether customer will stay or customer will shun. in telecommunication, so you could have people moving from one network to the other. And in different other marketing situations. So logistics can help you to predict whether a customer will shun or not shun. In the election too, so you could, if you have a candidate, so you could also use the logistic regression to predict whether the candidate will win or lose. Several application areas. You cannot even exhaust the list. Any questions so far? Any question? We have a very long way to go. Yes. Is somebody talking? Yes, Badmos.
Good morning, sir, Prof. Thank you very much, sir. Sir, when you are telling us about the difference, you made mention of binary, that the dependent variable of logistics uses binary. That is, the outcome is on binary, either 0 or 1. And when it's come to the other one that you mentioned is it uses logistics. The function uses logistics. That's where I have the question, sir. My question is that the logistics that you use, is it based on the probability that the probability of a particular function is certain, that the probability of certainty which is 0, or certainty which is 0 and certainty which is 1, is it that one that it works on, or the 0 and 1 as what we use as a assigned variable to the random variable, as function that we assign to random variable? That is does it uses 0 and 1 as a function we assign to it, that 0 represents for, like, where we say someone has a disease, 0 means that they have the disease, 1 means that they don't have disease, or the function that it uses is that the probability that they will have disease is 0, or probably they will not have disease is 1. So that's what I want to get, sir.
Yeah, that's even the next thing we want to discuss. So the logistic function, I mean, you know about the linear function. So if you
Yes,
talk
sir.
about
I know the linear. Yes, sir. I
f
know
of y, for instance,
I know. Yes, sir.
say that is a plus bx.
BX.
So
Yes,
in
sir.
this case,
I'm
so
getting it, sir.
okay. So, but this one assumes that your y is continuous. Now, in the logistic function, this is also like calculating probability that y takes a particular value. So this is probability that y takes, so let's say y1. So this is also calculating probability. But you know your y here is continuous. So
Yes,
it
sir.
can take any value. But where you are calculating probability of y, and your y can only take 0 or 1. There are only 2 possible values that y can take. So it can take probability of y equals to 0, can take probability of y equals to 1. I hope I'm communicating with you.
Yes, sir. I'm getting you, sir.
So the function that is used, generally the function will then become 1 all over 1 plus the exponent raised to power minus maybe x rather. So this is the general expression for a logistic function, just as this is the expression for a linear function. Is somebody trying to say something? Okay. So this is expression for logistic function. So this function, in a way, is a function that constrains this expression to lie between the value of this, because you are talking of probability now. So
Yes, sir.
yeah, so it constrains this to lie between 0 and 1. So if you, I don't know if that answers your question, but the point,
you really answered my question, sir.
The point now is that we are talking of different functions. You know, you have linear function, you have Poisson. If you are dealing with a dependent variable that is Kant, again, you will be using Poisson. And so the function you will use will be the Poisson probability density function. So logistic function has this kind of expression. So that is why here now you have the expression, the logistic function defined as given in that expression. So there are two possible outcomes, and usually the outcome that you consider as your success out of two, for instance, in tossing a coin, you consider if the head appears as your success, that is assigned the value of 1.
Okay, sir.
And the other one is the probability of failure. So in logistic regression, probability of y equals to 1 is the probability of success. And therefore, that probability is written now as 1 all over, this part. So this part is that expression, actually. That expression. So this is actually, this should be so this should be 1. So this is now replaced here with 1 all over 1 plus e raised to power the linear component, because you always write your y to be equals to whatever. This is the linear component. So
okay, sir,
minus the linear component.
Okay.
Right. So that is why we call this expression the transformation. When I was talking the other time about the transformation function, logistic regression uses the logistic function. It uses the logistic function to do what? To bind the response to values that will lie between 0 and 1. So this expression is borrowed from the logistic function. This part that you see, beta naught, that is the linear component. So it's transforming that linear component. It's transforming that linear component. So probability of y equals to 1 is the probability that the dependent variable will take will take the level that we consider to be success. So unlike the linear regression, your y is continuous, but in logistics, your y is going to be converted to binary variable, which will be 0 for failure and 1 for success. Then the coefficient of the linear components, beta 0, beta 1, beta 2, that's what you see in that expression. The x's are then the independent variables or the features that are considered to affect the probability, that will influence the probability or the chance of that particular outcome occurring. Is it clear, or if there is any other question on this before I move forward? Cynthia, I can see this class is. Hamid, is it clear?
Yes, sir. It's clear, sir.
Okay. Osareme. Osareme.
Yes, sir. Yes, sir. It's clear, sir.
Okay, so I'm good to go. Let's continue. So advantages of logistic regression. One, I've said it. It provides the probability, so you can easily compute probability that the probability of a particular level occurring, or the probability that a success outcome will occur. Again, when it comes to the ability to interpret, it's easy to quantify each impact, the impact of each independent variable on the probability. So in other words, from the estimation of the coefficient, you are able to assess the impact of the variables on the probability. Then with regard to computation of the parameters, the coefficient, you will agree with me that it's not as easy as linear regression. So linear regression is computationally more efficient, compared to the logistic regression. But logistic regression is also easy to implement. It's not as tedious as other techniques. So only that if you compare the efficiency with that of the linear regression, is a bit computationally intensive compared to linear regression. But the advantage there is that there are a lot of computational tools that have been developed to make it less expensive and very fast. The limitations include the fact that it's limited only to the dichotomous variables, only 2 variables. Remember, it's because for now we are focusing on only 2 classes. We could have situations where you have 3 or more levels. So then, as far as another limitation is that is is only assuming linear relationship, not between the dependent variable and the independent variables, or the features in this case, is not assuming linear relationship between them, but it's only assuming linear relationship between the logic. The logic itself is the expression for transforming the outcome variable to probability. So it's only establishing linear relationship between that logic and the predictor variables. So not between the dependent variable in its, in its actual form and the dependent variable. So in other words, between the actual variable, the dependent variable itself, and the features, you actually have a non-linear relationship. So those are the limitations. Now let's go to the mathematical foundation of logistic regression. So this expression now is the logistic function that I was trying to show you the other time. That expression is the logistic function, where you have the sigma t equals to 1 all over 1 plus e raised to minus t, right? That is the logistic function. And then the t there, this time around, that function is the one that is transforming the linear, that t, let me say, is the linear combination of the independent variables, which is expressed as t equals to beta naught plus beta 1x1. So that's the linear combination of the predictors of the explanatory variable. So that logistic function, sigma t equals to 1 all over blah blah, is actually mapping any real value number, is transforming that expression to a number that lies between 0 and 1, making it easy for modeling probability distributions. So, in other words, the logistic function itself is a transformative function, and it's a function that helps to transform the linear function, to compel it to lie between 0 and 1, so that if you are now predicting, you will not be predicting values that are outside 1 or values that are negative. If you are using linear regression to predict, you can predict values that are even outside the range of the observed value. But it's not going to be possible in logistic function. So your predicted probability will be forced to lie between 0 and 1. So if we go back to the expression that I talked about earlier, so even though you have probability So if this is probability of Y equals to success, and then probability of Y equals to failure, you can also see this as probability of Y equals to 1. So a success outcome is equals to is assigned 1. Probability of Y equals to 0. So this is the probability of success. This is the probability of failure. And therefore, the ratio of this probability of success over the probability of failure, you know, I can also write this probability of failure as 1 minus probability of success, since they must add up to 1. I hope you are following me. Since they must add up to 1, I can
Yes, sir.
also write probability of failure as 1 minus probability of success. So 1 minus probability of success, Y equals to 0. So this expression, which is probability, which you can also call probability of success over probability of failure, is what we call odds. Is what we call odds. So if you are defining the odds of an event occurring, then it is the ratio of the probability of the event occurring over the probability of the event not occurring. So what if I say, what is the odd that it will rain today? Who is going to tell me what is the odd that it will rain today? Yes, Badmus.
Yes, sir. The odds that it rain today is probability that there will be rain today over probability that there won't be rain today.
Excellent. So it is the probability that it will rain, because it's either it rains or it does not rain. So the ratio of the probability that it rains, which is probability that it rains over the probability that it does not rain, that is what we call the odds. So when you calculate the odds, then you are able to know the probability of the event, the event occurring. You are able to assess the chances. You are able to assess the chances of it raining, and that takes us to the second level. So if we have defined odds as the probability of Y equals to 1 over probability of, of 1 minus probability of Y equals to 1. Remember, we have defined probability of Y equals to 1 previously, but don't worry, you have defined that probability before. So this is the definition of odds. But the definition of the log of odds, which is what we actually call logit. So I'm only taking the log because This expression, if you go back, that is going to, this probability is on its own 1 over 1 plus e raised to power minus, this time since we are using y. That is the expression for probability of so if y equals to 1, this thing will also be equals to 1, but let's just leave it as y. Then this will also be 1 minus 1 all over 1 plus e raised to power minus y. So you can do your mathematics. I leave that to you. But let's come back here. So when I take the log of the odds, then I will have logit to be equals to the log of everything here, probability of y equals to 1 over 1 minus probability of y equals to 1. So this is what we call logit. This is what we call logit. And therefore, has anybody been able to resolve this? If you look at this expression, if you look at this expression, if you look at this expression, this is 1 all over 1 plus e raised to minus y over, you know, this is a fraction here. So you can take the denominator to be 1 plus e raised to power minus y. And then this will be 1 minus e raised to power minus y. Sorry. Huh? You have resolved it. So I'm happy that, so somebody has done it, and that's where I'm going. You can also do the manipulation. So you can see that everything here, everything here will give you what? 1 over exponential. So everything here will be equals to 1 all over exponential minus y. Exponential minus y. Yes. So, and this is minus, what will it be at the end? This is going to be e raised to power y, true or false? At the end, that will be e raised to power y. Now, which means my logic is equals to log of e raised to power y. And what is that going to be? Logit is equal, what will, if I take the log of e raised to power, that will be y. Isn't it
y.
so? That
Yes,
this is y. This is y. And therefore, our model become logit, which is defined as this, equals to y. Our y is beta naught plus beta 1 x1 plus beta 2 x2 plus dot 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 up to beta k xk. So which means this logit has been transformed to have a linear relationship with the predictors. The logit has now been transformed to have a linear relationship Mind you, it is not y that is having linear relationship with the x's any longer, but rather it is logit that is having linear relationship with the predictor variable. Is it clear up to this point, everybody? Is it clear?
Yes, sir. It's clear, sir.
Sorry. Yes, sorry, I was attending to something. Is it clear, everybody?
Yes, sir.
Yes, sir.
Yes, sir. It's clear, sir.
Okay, I've not heard from Badmus is yes.
Thank you,
Badmus,
sir.
what's it?
Thank you, sir. Thank you, sir. It is clear, sir. But, sir, since we use y, we take the logit of the function and it transforms back to y, which is also assumed to be the dependent variable.
To
Oh,
be
there will
linear
be
combination. Linear
linear
combination. It's
combination.
not just
Okay,
yes,
okay, because that's what
yes.
I'm thinking. I hope it should not return back to the actual that y from the beginning.
No, you know, in our linear regression, we use y to represent the linear combination of the x's. I don't know if
I
I'm
understand what you
confused.
say, sir.
So if you take away this part, then you say is equal. This is what we know to be y, right?
Okay, sir.
That's what we know to be y, and
Okay,
it
sir.
is the linear combination. But what we are saying is that logistic function has now transformed that linear combination, right, to become logit. That's what we have done. And this logit is now the one that is linearly related, but not y. So, therefore, you must understand the meaning of odds and how odds, the log of odds, becomes the logit, and that is the model we now want to estimate. So it is this logit function that we want to estimate. So how do we estimate it? We use the maximum likelihood method, because you can't use the OLS because that function is non-linear. It's a function that is non-linear because it's going to be a function that will, the highest value it will take is 1, and the value, this is 0. So it's probably going to take something like this. So it's not going to exceed 1, and it's not going to cross to negative side. So that is it. So it's going to take value that will never be equals to 1 exactly. It will keep approaching 1, so to say, but it will never. So you will have the logic here, and then you will have the x's, or maybe your linear combination, your y, here. So it will never become 1. So that function is non-linear. A linear function will go straight like this. A linear function will go straight, or will either go upward from left to right or downward from left to right, whichever is the case. And a linear function can even be, you can take any value on the continuous scale. It can be negative, you know. So now that is the likelihood function is expressed that way. You know how to take the likelihood function and so on, but it's just to give you the procedure. We are not going to waste time on that. So after fitting the model, of course, the model does not have a closed form solution. Unlike the linear regression, it has a closed form. When we say something has a closed form, what does it mean? Huh? Speak louder, Joseph.
It's something that has an end, beginning and end, when it has closed form.
When a function converges, then it's said to have closed form.
No way. Who is helping us? Who is helping us? If we say it has a closed form, yes, Osareme.
I was saying that when it's have a closed form, so that when it has a beginning and has an end, so something is close.
No way. You are telling lie.
Oh.
That's a closed form solution. It has a closed form solution.
Can I? Okay, sorry.
Yes, Professor.
No, I know I was so wrong, but I think it's the solution will be exact rather than being an approximate or a range of
exactly,
values.
which means there is a formula. You can there is a formula that will give you exact value. There is a formula in the OLS. Each coefficient, you can derive the formula. For instance, in two variable regression model, one dependent, one independent, you know that the coefficient of beta is equals to the covariance of x and y over the standard deviation of x. So you can easily use a formula to obtain the estimate. But when it does not have a closed form solution, you will now resort to numerical iterations. You will now resort to numerical iterations to be able to find the optimal numerical solution. So, and that's what we do in the maximum likelihood. So there is no closed solution because even if that expression likelihood function of beta, if you differentiate it as we used to differentiate and equate to a zero, you won't be able to get a single formula. The only thing you can now do is to use numerical optimization techniques to now look for the combination of betas that will give you the maximum likelihood function. The beta that gives you the maximum, that's why in the maximum likelihood approach, the criterion is you are maximizing the likelihood function. In the ordinary least square approach, you are minimizing this residual sum of squares. So numerical optimization techniques helps you to obtain the parameter values that maximize the likelihood function that is given there. So instead of talking of residual in in logistic regression, you cannot actually talk of residual the way you talk of residual in the linear regression model. So you talk about deviance. So the deviance, that's the departure, you know, from the departure from the predicted logic. So that gives you the model's goodness of fit. So it's similar to residual sum of squares in linear regression, but we don't call it residual, but rather deviance. So the other measure which we use is the pseudo R square. In the linear regression, to evaluate the model performance, we use the R square, right? But in logistic, we use the pseudo R square, which is calculated as 1 minus residual deviance divided by the null deviance. Residual deviance is the one we talk about. The null deviance is the deviance arising when the logic is, when the model does not use any of the predictor variables. So it's not deviance. So it will look at the ratio of the residual deviance, that's deviance arising when you use your predictor variables, and deviance arising when none of the predictor variables is used, and then take that ratio from 1. So that is the discussion on the computation of odds, logit, and then the estimation of the parameters, as well as the measure of goodness of fit. I hope that is clear. Then what is the procedure for developing the model, and what are the underlying assumptions? So the starting point, if you are going to use logistic regression, the starting point is to prepare your data. So as usual, you have variable selection. What variable will be my dependent variable? What variable will be my independent variable? Then you carry out, you hypothesize the influence you expect among the variables. What do you feel should be the relationship between the dependent and the independent? That's what you do when you are hypothesizing the influence. So, in other words, the starting point is data preparation, and data preparation has 2 major components: variable selection and then data cleaning. In variable selection, you say, what will be my dependent variable, which must be binary, no, yes or no, alive or dead, depreciate or not depreciate, and so on like that. What will be my independent variable, which variables are potential drivers of the dependent variable? What are the things that can cause, if we are talking of depreciation, no, what are the depreciation or appreciation of Naira? What are the things that can cause that? Maybe our level of foreign reserve, maybe the inflation, maybe imported inflation, maybe our output, maybe whatever. Yes, can you help me more, Dr. Olowo Kere? We need your expertise now.
No, You have done well, sir.
Thank you for marking me, for grading me. So, am I correct? I mean, our foreign reserve, maybe that will also affect. Maybe our level of output, maybe that will also affect. There might also be, I don't know, maybe imported inflation, if that can also be factored in. Maybe oil price. These are ordinary layman ideas.
You know, they are beyond layman, sir.
Oh, really? People like Joseph can even give better ideas. People like Amit, Femi, and Co. So that's how you formulate your. That's how you formulate your. Sorry, Johnson. So sorry for that. So data preparation involves variable selection, data cleaning. Then two, you now do the feature engineering. Feature engineering involves transformation. That is, you now have to convert the categorical variable into dummy node. In fact, we are starting this from today, everybody. Somebody should please, maybe Dr. Olowo Okere, you are going to, Joseph will create a Google Doc, a Google Sheet, and share with the class. From today, we want to start monitoring the Naira dollar exchange rate. We are not, you can record the exchange value, the exchange rate value. Then you will also decide whether it appreciates or whether it depreciates. So then alongside, we will also be observing some other monetary indicators, or so Dr. Olowo Okere will guide us into those potential things that predictors that we can be guiding. So I hope that is okay, Dr. Olowo Okere.
That's fine, sir.
So that may be our own. So let's be observing. We will monitor both the exchange rate for the parallel market, as well as the official market. So, but the other variables, you will help us with that. So everybody in the class will have to participate. We will do this every day, monitor the exchange rate, and then by the time we have up to 30 days or more, then we can do a bit of analysis using our model to predict whether. So we can create a dashboard such that this thing will automatically update itself. The algorithm will continue to learn as we have more and more observation, and then we'll be predicting the next day outcome, whether the next day outcome will be depreciation or appreciation. So that would be something for us to, as a class activity. So Joseph and Amit and Ese, supervised by Peter
Bless.
and Blessing. Those are the people I will hold responsible. You will need also to consult with Dr. Lowo Kere to guide us in those daily macro indicators that we can
Data sourcing.
alongside. So we will create our database on Google Sheet and we will continue to populate it on a daily basis. So you have to monitor this thing. Then we will be using artificial intelligence coupled with a number of other things to predict what what will be the outcome, a day ahead or few days ahead. If you are not happy, let me know.
It's fine, sir. It's okay, sir.
I said if you are not happy, I'm not saying.
We are happy with it, sir. It's okay, sir.
Nobody is unhappy. So, but if you are not happy, just let me know. I have a better assignment for you. So, this time we have determined what our dependent variable, our independent variables will be. So later we will clean the data, look for missing values, look for outliers, and so on. We'll format. Then we will do feature engineering if we need to convert. So we will need to convert our dependent variable, which will always be depreciate, appreciate, depreciate, appreciate. So we convert it to dummy variables. So we will use one for appreciation because we can consider appreciation as our success, and then the other one will be 0. So we create a new variable that will just be 0 or 1. Then we will do the scaling. So the scaling might be to convert all the variables, to have the same unit of measurement, whatever, so that we have consistent units. We can do that if necessary. It's not compulsory as far as logistic regression is concerned, but why not if not? Then we move to model specification. So this time we will define our logistic regression equation with the variables that we have decided. So our logic will be probability of exchange rate, appreciating, exchange rate equals to 1, which will mean probability of exchange rate equals to 1. And then we will now write the linear combinations, B0 plus beta 1 times the foreign reserve, then plus beta 2 times GDP or whatever we take as industrial output, whatever we want to use, we'll use that. And then we specify our model. We can now hypothesize the kind of relationship we want, we expect between appreciation and foreign reserve, the kind of expectation we expect, we hypothesize what to expect between industrial output and appreciation, and so on and so forth, like that. So estimation is then the next thing. So that's where we apply the software. So we are going to use the R software, and then you will learn how to do the coding. Anything. So then after estimation using the software, we will now have to do model refinement. Model refinement might require that we look at variables that we need to select and variables that we need to jettison. In fact, we can have several variables in our that we will be observing, not just 1, 2, 3. We can have as many of them as possible. So even if we have more variables than the number of observations, that will lead us to use the penalized binary logistic regression. We have discussed about penalized regression. So it's not applicable only to linear regression. We can also use penalized, ridge, elastic, and then the lasso regression in binary logistic regression. So we can use it if we have more variables than the number of observations that we observe. Then we may want to consider adding interaction terms and provide justification, theoretical justification for that if necessary. So what are the key assumptions of logistic regression? One basic assumption is this binary outcome. The dependent variable is binary. So, meeting. Key assumptions. One, binary outcome is very important, and that assumption must be satisfied. Two, linearity of the log odds, which is the logit. That is, we expect that the logit and the linear combination of the dependent variable must be, the relationship must be linear. So, we must ensure that there is a linearity of independent variables and the logit. Then the assumption of no multicollinearity is very, very important. And we are going to see how to check for these assumptions. Then there must be no significant outliers in our data set that can influence the effect of the regression estimates. The estimate of the coefficient. Then we need relatively large sample size. We need sufficiently large sample size to ensure reliable results. So these are assumptions which you must ensure that they are well satisfied. How do we check for this assumption? For number one, binary outcome, you need to shine your eyes. There is no formula for checking that. Just use your eyes and use your intelligence, use your brain, and don't borrow somebody else's brain to check if it is binary outcome or not. Then, but for checking linearity, you can use Box-Tidwell procedure to check for linearity. You can do your research work on that. So check for Box-Tidwell procedure to check for linearity of the log odds. Then assess the multicollinearity. You can use the variance inflection factor to check each predictor. So once the VIF exceeds 10, then there might be a need for concern. So you calculate the VIF, and if it's below 10, don't worry yourself. So 3, how do you handle outliers? Then you can examine the leverage and influence plots, which you can always get as part of the output. So you look at the residual plot to check if if there are outliers or if there are influential observations. Finally, to ensure adequate sample size, the rule of thumb is that you have at least up to 10 observations, 10 cases per predictor, so that statistical power can be maintained. But you need anything reasonable. So don't have just 5 observations and be, or 6 or 10 observations and be running logistic regression. How do we interpret? Yes, this is very, very important. But before we discuss this, any quick question? Any question? Any question? Any question about data preparation, about assumptions? Any question? Any question? Femi, no question. Some people have left. Maybe internet. Yes.
Because of the internet. It could be because of their internet. So my own question, I reserve it to the end. But it's just about the statement you made that logistic regression cannot be used to predict for future realization. You said
Did I
it's
say
when we
that?
are like we can't, because you said you can only capture the data alone.
No, well, did that? I think you have to quote me
Maybe I'm
correct.
not listening
Quote
very
me
well.
very well because this thing is being recorded.
Okay.
So what did you hear? Let me know so that I can edit if I, yes.
Okay.
What did you hear? What did you hear?
Okay. Maybe that
Did I
I
say
heard that.
yes?
Okay, logistic regression
Yes.
can't like make future realization, like future prediction.
Did I say that? I said we will even be using it to predict future possible outcomes of exchange rate, whether it will appreciate or it will not appreciate. So we will be able to compute, for instance, tomorrow or future ones, whether what will be the probability that it will appreciate or whether it will depreciate.
Okay, sir.
Yeah.
Okay, sir.
Yeah, bad news.
Okay, sir. Thank you, Prof. Thank you, Prof. Sir, Mr. Jasa, what Prof was saying that time is that we will even, the statement is that we would even use it for prediction, future prediction. That was when he mentioned about the exchange rate of a thing, and he said, Joseph and you, we have to create a Google sheet whereby we use it to monitor this exchange rate, and he made mention of Dr. Polabi to join you guys to also contribute to it, to supervise you guys with blessing. So not like we will not use it for prediction. Ajasa, hope you heard me, sir.
Okay.
And
Sir.
that's
Thank
what
you.
Prof said. Yeah. Thank you, Prof. Continue, sir.
Thank you, Badmus, for saving me from the clause of yes, Joseph.
Just a question on this, that when performing feature selection, are we to transform the dependent variable or the independent variable, sir? Which of the variables are we transforming, sir?
In the discussion, the emphasis, you have to, when you are recording your data, you will be writing appreciation, depreciation, and so on. Then you have to now create a new variable, which we now use 0 for depreciation, use 1 for appreciation. So that variable is like you are recoding the original one, you are recoding it. The string one, you are recoding it now to numbers of 0, 1. So it's not changing anything, only that you are converting the string word or the text to now numbers. So using numbers for the different 1 for appreciation and 0 for but for the predictor variables, I said you can do scaling, you can do any other form of transformation. For instance, if there are multi-collinearity, if you have multi-collinearity, you might have to use principal component analysis and to address the multi-collinearity problem. So there might be need for transformation, to get rid of the multi-collinearity problem. Does that answer your question?
Very well, sir.
Okay. So let's go on now to interpretation of model outputs in the regression, in logistic regression. It's always an interesting thing. So when you have estimated the model, the coefficient that you get is actually coefficient that you cannot interpret. So because you need to transform those coefficients before you can interpret them. So if, for instance, you get a coefficient, that is for beta 1, for instance, then you can only say that beta, if the coefficient is positive, then you can only say that that coefficient represents the rate of change in the logit. The rate of change in the logit for every unit change in the variable that is attached to it. And that does not make any serious any meaning, because logit itself, there is no meaning to that. So the only way to make it meaningful is usually by using the log odds. So, and to get the log odds, you have to take the exponent of that coefficient. So you will take the exponent of the coefficient, and that is what you do under the transformation to odds ratio. So by taking the exponent of that log, then you can now be able to interpret in terms of the odds ratio. So if the odd ratio is greater than 1, then it indicates that the predictor actually increases. It indicates that as the predictor increases, then the chance of the outcome we consider as success occurring is more likely. Conversely, If the odd ratio is less than 1, then it suggests a less likely occurrence. So this is how you interpret. But that will take place. So if beta, for instance, is the coefficient of age variable, and after estimation, the age variable, the beta is equals to 0.2, then you will now need to take the get the odd ratio by taking the exponent. So the exponent of 0.2 is giving you 1.22. And since 1.22 is above 1, then it suggests that each additional year of age, remember age is the predictor variable. It suggests because the odd ratio is now above 1. So it suggests that each additional year of age, for each additional year of age, the odds of the event occurring will increase by 22%. So the converse will be the case if, for instance, the value is less than, let's say, 0.22. Then it will mean the odds of the event occurring will decrease by that percentage. Will decrease by that percentage. So we will see more of this interpretation when we look at an example. Then there are critical tests, significant tests, and confidence intervals that you need to know. As usual, you know how to interpret p-values, confidence interval. You can always do that. Then the pseudo R-square, you can also interpret measure the proportion of variance in the dependent variable that is predictable. You know how to interpret all of that. But there are several pseudo R-square measures: McFadden, Cox and Snell, Nagelkake R-square. So these are all pseudo R-square, and they can also be interpreted the same way. They measure the proportion of variance in the dependent variable that is predictable from the independent variables. But you should not interpret the way you interpret the R-square in linear regression. So if you are interpreting this, you must be comparing them with another model. So they only make sense. Don't say the way you interpret R-square to say it is the percentage of
percent of the total variation.
Yes.
The proportion of total variation in the dependent variable as a result of the independent variables in the model.
Okay, so you cannot interpret in that sense. So what those McFadden, those pseudo R-square, you can only use them to compare two competing models. Let's say in our model, let's say in this model, for instance, in this model logic of probability of shunning equals to 1, you have age, you have monthly charges. That's one model. You can get a pseudo R-square for that model. Let's say you have another model, beta naught, beta 1 times age, but you don't have monthly charges. That's another model. You can now compare the pseudo R-square of these two. The one with highest pseudo R-square will be preferred. So That's the usefulness of those pseudo R squares. I hope I'm clear.
Yes, sir.
Great.
Yes, sir.
So use them to select features or to select best model. So they only measure model quality in a relative sense, not to interpret them the way you interpret R square. So most people commit that error. You can also compare the likelihood ratio. You can use likelihood ratio test to test whether by adding additional predictor, it improves the model significantly or not. So it's another measure of fit. There are advanced diagnostics for the advanced diagnostics. Osma Lemeshow test is also a goodness of fit test. You also use the area under the curve, ROC, receiver operating characteristics measure. You can also use that as a way of diagnosing your model. I have two practical tips for interpretation. I've always been advising you to put context to your analysis. Don't interpret without putting context, without you connecting your model to a particular context. So your analysis must actually address your research questions and the data. Don't go beyond what the data is saying. Don't overgeneralize. Don't go outside the context. Our concern is about exchange rate. So if we are dealing with dollar naira exchange rate, and we do this our analysis, we cannot generalize to naira pound sterling exchange rate. That is out of context because our data does not cover, our data does not cover that particular currency. So you always put context to your research question, limit your interpretation to your research question, and don't go outside the area of your, don't go beyond what the data is saying. So, of course, you can bring in your domain expertise into the discussion, but even at that, you have to be cautious and let it be clear that this is what you feel as an expert, but not emanating from the analysis. So again, bring your theoretical knowledge into being. So you can use theoretical knowledge to counter argue the result back and front to be able to be objective in your presentation. Again, avoid causal inference. So causal inference in logistic regression, people do a lot. When you are saying, for instance, maybe your result shows that a foreign reserve is it causes naira depreciation and so on. Your model will never also tell us whether depreciation or appreciation causes foreign reserve to grow or to uh, 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 decrease. So causal relationship cannot be established with logistic regression, but cause and effect relationship can be established. There can be a cause, so our predictors are causes. And the effect is the state of the outcome variable, which is depreciation or appreciation. But the reverse is not the case. So effects are not also causing the causes. So that must be well noted. Avoid causal inference very seriously. I hope that is clear to us. So I think, yes, is there any? Yes, Ayodele.
Thank you, sir. Good morning, sir.
Good
Please,
morning.
I would appreciate if you could make a clearer distinction for me, particularly when you mention causal inference relationship and cause and effect relationship. Is there a major distinction between that? Thank you, sir.
Okay. When you have your model y equals to maybe f of x, so this is saying that okay, maybe you have your x1, x2, x3, and so on. We call this one, these are the causes, and this is the effect. So in a linear relationship, we can only talk about cause, effect, relationship. So in other words, this can be your consumption, for instance, and this can be your income. Yes, we can say that your income will determine your consumption. And that's what this model is saying, that if I know your income, then I will know I can predict your consumption. There could be other variables, so holding them constant. So here we are talking about cause effect relationship. So the relationship is from X to Y. The relationship is from X to Y. And that is what any regression model is doing. That's what any regression model is doing. Now we could have a relationship that is both ways. So it's from cause to effect and also from effect to cause. This is both ways. So this is causal. This is causal. Causal is two directional. Yes, this one you can say is correlation, or they are related. So correlation we only no don't say correlation, but is cause effect. This is cause effect. This is cause effect relationship. It's not causal. So the x's are causing y, but y does not cause x.
Like Ganga causality in
Eh?
econometrics.
Eh?
Like Ganga causality.
You want to draw us into econometry. So now I want you to think of two phenomena in life that are causal. For instance, okay, before we look, let's think of cause effect. They tell you now, if you smoke, if you smoke, you are liable to have cancer. So yes, so smoking can cause what? Cancer. But cancer cannot cause smoking. So you can have uh, a one direction kind of relationship. A one direction kind of relationship. But there are instances where you could have A causing B, and simultaneously B is causing A. I can't really. Is anybody able to think of one example quickly? A causing B and B causing A.
So can we say that as a result of your good feeding, you can have a good health, and being
Let's use variable. You have to define the variable very
very
well.
okay.
Like, okay.
Yeah, so you can talk of diet,
Diet,
right? Diet
yeah,
can cause good health, but
good health.
good health, you can't say good health will cause diet. You can, if you, yes, essay.
So I just want to try. I don't know if I'm correct.
Try now.
For instance, let's say your performance in your work environment
Yes.
sometimes can determine your pay if your employer can decide to increase or decrease or even ask you to go in an organization. Then
Okay.
if there is a constant increment in salary, the pay, it can also motivate the employee to perform better.
Okay. So you are saying that work performance can influence wage,
Increase in pay, yes sir, yes sir.
and then wage can also uh, uh, affect productivity, work performance. It looks good. Looks good. So there might be a two-way direction, between wage and productivity. So if you get more paid, then you produce more, and if you produce more, maybe you can also get more pay. That sounds uh, it looks good like that. So, but I think the Ayodele, you get the gist, right? Our time is going. Ayodele, you asked the question.
Yes, sir.
Okay, so wow, this is 10 o'clock. and I have another meeting at 10. Okay, so I think we have done justice to most of the issues. I put these advanced topics in logistic regression, not necessarily just to put you on your toes. So I said earlier we could also use lasso regression, ridge regression, elastic regression in logistic regression. So you can have lasso logistic, ridge logistic, elastic logistic regression. So good enough, you have examples. I use, so you have the code snippets for R. You can use the GLM function in R to run logistic regression, get the confusion matrix. The confusion matrix will give you false, the true positive, false positives, and all of that. Then you can get the ROC function and the AUC. Then you do your diagnostics to check residual, check for multicollinearity. So the codes are there. To check for linearity, you can also always use the, so if you run this, it uses the car data, the car, there is this, the car data set that comes with R. So try to run this and practice and interpret the results. Then I use another data for practical demonstration. That's Titanic. Oh, I wrote Titanic, not, it should be Titanic, sorry. It should be Titanic data set. I'm sure you heard the story of Titanic. So I share the data on our on our Google Classroom. You will see the data set on for training and for testing. This is the training data set for Titanic. This is the test data set for Titanic. Try to do that. You will see my results here. I also try as much as possible to interpret those results, go through my interpretation, and also I fitted the model, which is the dependent variable is whether the passenger survived or not. So the variable name is survived. Then other variables as predictor is the class, the gender, the sex, the age, the port of embarkation, and so on like that, were used as the predictor variables. And then this, you have the results, and we can see that the passenger class, sex, and age really determine or affect the survival of the passengers. Then we did, so the results are fully discussed. I hope you will take your time. Then we validated the model. These are the results. This is the confusion. You also have the confusion matrix, which are interpreted. They are the true negatives, the false positives, and so on. And all the statistics are also well discussed there, just to help you understand this. And finally, we make predictions, Amit. So we made prediction that if we know from the test data, we try to predict whether a passenger will survive or not. So the first 6 predictions shows that only one will survive. So that's the end. And then you have your own practical exercises. There are 2 questions that I have here for you to practice with to show that you understand. And then the multiple choice questions have been uploaded for you. Thank you, and sorry for taking extra time. You also didn't come on time. So,
Thank you very much, sir.
Thank you so much, sir. We'll appreciate, sir.
Thank you very much.
Thank you, sir.
You are welcome. So, there is no question. This is a good place to stop the lecture today. Enjoy.